Number 1. Describe what it means if there is a model breakdown when using a linear model. So with these linear models we have a certain domain and range, and for example, time could be the domain and the model might be valid for a certain amount of time but no more than that, or the reliability of it may be called into question. So if we try to make value predictions outside of the domain or range, there may be problems with that, there may be pitfalls. So when our model no longer applies after a certain point, it's sometimes called model breakdown. Number 3. What is extrapolation when using a linear model? Well, that involves predicting a value outside of the domain and range of the data. So your extra meaning outside, as opposed to interpolating, inter meaning inside. Okay. Number 5. Explain how to interpret the absolute value of a correlation coefficient. So the absolute value is basically disregarding the sign, that is whether it's positive or negative, and that indicates the amount of scatter. So the closer the correlation coefficient is to 1, the less scattered the data, and the closer it is to 0, the more scattered the data. So when you throw in the sign, positive or negative, that tells you whether the data is increasing or decreasing. Number 7. A regression was run to determine whether there is a relationship between the diameter of a tree, that would be x in inches, and the tree's age, which is y in years. The results of the regression are given below. Use this to predict the age of a tree with diameter 10 inches. Alright, let's write the information here. We've got y equals ax plus b. Basically that's your slope-intercept equation. You're using a instead of an m. Y equals mx plus b. Statistics often does that. They change the names of the variables for their own reasons. Alright, so when you get into other fields of mathematics, you might find that to be the case sometimes. They'll change the names of the variables, but it's basically the same thing that you've been working with all along. Alright, so they might use m for other purposes, right? Instead of mx, they'll use ax. So a is 6.301 and b is negative 1.044. And r, that's our correlation coefficient. In statistics, small r indicates correlation coefficient. That's negative 0.970. So the data fits this model quite well. It's close to negative 1. It's decreasing. And so we have y equals, so instead of an ax plus b, you put 6.301x plus b, which is negative 1.044, so that's minus 1.044. Alright. So what we want is well, let's see, what do we have here again? We have the diameter is 10 inches, so what we want is y of 10. 6.301 times 10 minus 1.044, and when you compute that you get 61.966. So the tree is about 62 years old. Number 9. For the following exercises, draw a scatter plot for the data provided. Does the data appear to be linearly related? So here's our data. And what I did was I plotted that using my computer. Much better than doing it on here. Take a lot less time and it's a lot neater, more precise, more accurate. So here are the data plotted nicely for you, and you can check the results yourself. So let's see if I'm getting it all in there. I have to pull it back a little bit. Here we go. Hope you can see. There you go. You'll notice there's a slight curve. It looks like it would fit a curve very nicely, a certain curve, and there are ways to determine curves instead of straight lines. But we're dealing with straight lines here. That's the simplest case. So it doesn't appear to be a straight line fit. You could probably draw a straight line in there and it would fit approximately, but this definitely looks like it fits a curve much better. So you would need more training in a statistics course to be able to come up with that. But for now, we'll say it's not linear. Number 11. So here's the data. And again, I plotted this using a computer, and I came up with this scatter plot. And as you can see, the data, it's kind of like the last data set we looked at in the previous problem. It is more of a curve than it is a line, straight line. So this does not appear to be linear. Okay, number 13. For the following data, draw a scatter plot. If we wanted to know when the temperature would reach 28 degrees Fahrenheit, would the answer involve interpolation or extrapolation? Eyeball the line and estimate the answer. So if you look at the data here, they list temperature first and time second, or rather time next. And that would indicate that they want the temperature to be the independent variable and time to be dependent. Usually it's the other way around. Usually you have time on the horizontal axis and the temperature would depend on the time, so temperature would be the vertical axis, but we'll deal with what they gave us here. Alright, so when will the temperature reach 28 degrees? Estimate an answer. So I plotted the data here. And let's see, the time, or rather the temperature, is horizontal, capital T, right there. Alright. And the time is a vertical axis, going up and down. So where's let's see, 28. So here's 25, 26, 27, 28 right there. That vertical line going up is 28. If you follow that up, oh, it looks like it fits right in at around there, 60. 60. Alright, so that's just a rough estimate, of course. So in these eyeballing type problems, if you didn't come up with exactly 60 but close to it, I would personally say that's okay. How close is okay? Well, that's a judgment call. Alright, but you'll have to talk to your professor about that. But anytime you involve estimations, answers will vary. Number 15. For the following exercises, match each scatter plot with one of the 4 specified correlations in Figure 9 and Figure 10. So for 15, we have a correlation coefficient R equals negative 0.89. Pretty close to negative 1. The negative indicates decreasing, and 0.89, pretty close to negative 1, so I would expect not too much of a scatter here. Alright, so you're looking for a decreasing data decreasing and pretty tightly together. So what do you think? Yeah, I would say it's that one there. Alright, this data here is increasing, so that should be a positive R, positive correlation coefficient. These two are pretty scattered. Alright, so I wouldn't expect that to be 0.89 as a correlation coefficient. Alright, so that would leave this one. Number 17, we have correlation coefficient R equals negative 0.39. So that means, well, it's not very, it's closer to 0 than it is to negative 1, so that shows relatively large scatter. The negative indicates decreasing relationship here. So we're looking for something decreasing, and it's pretty much scattered. Alright, it's quite scattered. So if you look at the data, this tends to go up, it seems. So that might be a positive correlation there. And this one tends to, it appears to go downwards, so that's our negative correlation. Alright. This one's ruled out because it's positive correlation. This one is going downward. It's negative correlation, but it's too tight. The data is packed too tightly together. It's not very scattered, so I would say it's this one here, B, which it is. Okay, number 19. For the following exercises, draw a best fit line for the plotted data. So they're wanting you to eyeball it, alright? They're not expecting you to come up with the exact line of best fit. Not yet. We're not going to do that yet. So this is an estimation. So you try to draw a line that kind of fits in the middle of the data if possible. Here's what I got. Anytime you estimate one of these things, your answers will vary. Okay, so, and linear regression analysis shows you how to make mathematically the line of best fit where there will be no disagreement. It is the line of best fit for the data, but we're not at that point yet. We're just estimating here. So I noticed in the book's answer it's a little bit off or a little bit different from mine, which I expected. Alright, that doesn't mean it's incorrect, but you know, if you draw something way off of what the book has, then that might score against you, alright, if that were a test question. But when you do a linear regression analysis using the statistical principles, there will be no no doubt as to whether your answer is correct or not. Alright, so this is just for estimating purposes. So for 21, we also eyeball this data and try to get a line of best fit using estimation, and that's what I came up with. I noticed that it's a little bit different from the book's answer, but not much. So I'm happy with it. And for estimating purposes, that might be all you need. Alright, so again, if you want something really accurate, you do a linear regression analysis using statistical principles, and there will be no doubt as to what the line of best fit really is. Alright? Number 23. The U.S. import of wine in hectoliters for several years is given in Table 5. Determine whether the trend appears linear. If so, and assuming the trend continues, in what year will imports exceed 12,000 hectoliters? And here's our table. If you plot the data, which I did, I also plotted the line of best fit, but I don't want to talk about that just yet. So ignore the line of best fit that I drew here. But if you look at the data, the dots, those are the actual data points, all right, that I plotted, and it does appear to be linear. Okay, so it makes sense to do linear regression analysis on this one, which I did using technology. I used my old trusty HP28S calculator for this. Put the data points in. Alright, your calculator can probably do that if you have a graphing calculator. You can punch the data in there somehow or other. Alright, you'll have to read your manual, get help for that if you don't know how. You can go online and do this too, you know, look that up. Look up linear regression. And first of all, let's let the x-axis represent the year. That would be the top row in the data here. So the x-axis is the year, and the imports would be the y-axis data. Alright, so using technology, when you punch all that data in, you get the line of best fit, which I came up with as y equals 409 point, I'm going to write this all out in its glory, 5027 16523 x minus, continuing on the next line here, 813 comma 813,800 point 585491. All right. So also on your technology, graphing calculator, what have you, it should give you the correlation coefficient, and what I got was about, I'm rounding this off to 4 decimal places, 0.9848, which is a very good fit. In other words, this regression line that I came up with fits the data quite well. Alright. And there's a strong correlation. The data is not scattered very much around this line. Okay. So the question, when will imports exceed 12,000 hectoliters? How do you do that? Well, you set this, the equation for this line greater than 12,000, alright, so, and then solve for x. So we've got 409.5027 16523x minus 813,800.585491. Set that greater than 12,000. Squeeze that in here at the end. Alright, and then solve for x. So we've got 409.5027165223x is greater than, just add that to both sides. Alright, so you've got 825,000 800 .585491, and now you solve for x, divide both sides by all of that there, use your calculator of course. So what you end up with is x is greater than 2016.59366 879. So in the year 2016, alright, that's a little more than halfway through the year. Okay? Alright. Okay, number 23. This is a bonus problem that I'm going to do by hand. I've got that in quotes because I don't do it by hand all the way in every little detail. I do a lot of the arithmetic using a calculator, alright? But I'm going to show you how you can do this by hand, so to speak. Now the reference that I'm using for this is a book by Frederick E. Croxton. Frederick E. Croxton, and the name of it is Elementary Statistics. I'll just abbreviate that, with applications in medicine and the biological sciences. Alright, so I'm not going to write all that down, but it's called Elementary Statistics with Applications in Medicine and the Biological Sciences, and it's published in New York by Dover Publications. And if you're going into math or science, get familiar with Dover books because they're great, they're cheap, and they republish a lot of the old classics in math and science. They're always paperbacks. The old editions are really made well, very durable. The older ones recently, well, they're still durable, but not as much as they used to be. But This one was published by Dover in 1959, and I'm looking at pages 114 to 126 for this information that I'm about to give you. Alright, this was originally published before Dover got a hold of it, and that was in 1953, so this is an old book. This is pre-calculator days, alright? So this is how they used to do it routinely, alright? They didn't have fancy graphing calculators. They didn't have any well, they had calculators, but they were mechanical, or slide rules, alright? So with a slide rule, you can, well, let me show you mine. Here's a post-Versalog slide rule, and the center portion will slide back and forth, alright, and the markings are very precise. They're engraved very, very accurately. It's done with a logarithmic scale, okay, so there's some art and some skill to use these. It's got both sides do different things. You can do trig, but with a slide rule you can multiply and divide essentially, alright. If you want to add and subtract, you have to get back in the day you had to get a mechanical calculator. They had those that would add and subtract as well, and you can quite often find those on eBay nowadays for low prices. So that's probably the way they did these, alright? So what you do is you first make a table with the data. I'm using the same data that was in exercise 23 in your book, but I'm arranging it in this table. I'll show it to you rather than draw this on the glass board. So take a good look at that. Alright. So the data number, that tells you how many data points there are. There were 10. Alright. And the X column here shows you the year, and the Y column shows you the imports. Alright, so those should look familiar to you. Now x squared means you square the x's. You have to square those years. Alright, use a calculator for that. That's what I did there. Each one of those are squared years. Alright, so for example right there is 2006 squared right there. Square the y's as well. Alright, square the imports. So here we go down here. And then you multiply x times y. So just, for example, 1992 times 2665 gives you that right there, 5,308,680. Alright, and then at the bottom you total each column. So that's the total of all the x's, total of all the y's, and so on. You have to add all of those up. Alright? So each of those columns, you don't have to total the data number column. Just leave that be. Alright. So what we want is the regression equation. Y equals, I'm going to say y equals mx plus b. I'm not going to use ax plus b. Alright, that's what we want, is the regression equation, y equals mx plus b. So what we need to do is find m and b. Alright, and so to do that we solve two normal equations. It's called normal equations according to Croxton. They may use a different name nowadays for these. That's what Croxton called it back in the day. Alright, so let me write the normal equations out. Alright, so here's our two normal equations. This is Greek letter sigma, uppercase sigma. And in mathematics and statistics, it indicates the sum. So what that means is these are the sum of the y values, or the y totals, all right, which we already did in the table. All right, we already added up the y values. And this means the sum of the x times y values, or we already did that too. All right, that was the last column in the table. Add all those up and you get the sum of the x, y values. All right. So up here we've got capital N times B. Now remember, B and M, lowercase b, lowercase m, are unknowns. All right. So capital N is 10. That's the number of data points. All right. So you write 10b plus m times the sum of the x's. All right. We already did those. We added up all the x values. So you would write that number, whatever that was, next to the m. Okay. And then you would write the sum of x, y values here, which we added up, equals b times the sum of the x values. So you write the sum of the x values next to the b, plus m times the sum of the x squared values, all right, which we added up as well. You squared the x's and then you added all those values up, and that's what you would write there, right next. So what you end up with is a system of two equations in two unknowns, m and b. All right. Now you solve those using basic algebraic techniques, which you should have already done even before now, before precalculus, when you took algebra 1 or 2. You should have done systems of two equations with two unknowns. All right. So this is exactly what you have here. All right. So what do we have then? I'm going to fill in the data for you, the numbers. All right. So we've got 10b plus 20,009m equals 55,734. And then the second equation, second normal equation, is 20,009 b plus, this is kind of nasty here, we got 40 million 36,321 m is equal to 111,646,294. So again, this is just a simple system of two equations, well, and two unknowns. May not be as simple as the ones you're used to, but the principles of solving these are exactly what you've done before, or you should have done before. So you can do this by elimination. All right. It seems to me that it would be easiest to eliminate the b's here. All right, and then solve for m. So how would you eliminate the b's? What I need to do is get rid of that 10 and get a negative 20,009 there. So what we have is, if you multiply by, well, let's see, we've got 10b, right? We've got 10b. I want to get rid of that 10 and put a negative 20,009 in its place. So I multiply by a fraction with 10 in the denominator. That'll cancel the 10's out. And I put a negative 20,009 on top. So what that'll do is cancel the 10's and put a negative 20,009b in its place. All right. So again, you have to multiply everything in the first equation by, on both sides, by this number, negative 20,009 over 10. Okay. So I did that, and I'm going to write the results here as soon as I can erase all this. So here we go with more erasing as usual. Just bear with me here. Okay, so I get, after doing the canceling and so forth, I've got negative 20,009 B minus 40,036,000 and 8.1 M equals negative 111,518,160.6. Okay, and again, this just we'll rewrite the second equation. We've got 20,009B plus 40,036,321M equals 111,646,294. We add those two equations. So what happens is, when you add these two, the B's are gone. All right. So you add those two, you get 312.9 M equals 128,133.4. Solving for M, divide both sides by 312.9. So you get M is equal to 409.5027 16523. That looks familiar, doesn't it? Isn't that what we came up with using technology? Yeah, the exact number. Okay, now we can solve for B. We can use the first equation, that was 10B plus 20,009M equals 55,734. That first original equation. All right, so plug in what we have for M here. So we got 10B plus 20,009 times 409.5027 16523 equals 55,734. So multiply those two, subtract that from both sides, you end up with 10B equals whatever you get, all right? And then divide both sides by 10, so you get finally B is equal to negative 813,800.585491. Again, a familiar number that we saw before. All right. So this is in fact what we had for B as from technology. So you see all the trouble your calculator is saving you. So that's the result of solving the normal equations. All right. Now what about the correlation coefficient? Well, first of all, you might wonder, before we get into that, where do these normal equations come from? How do they get those? Well, that's beyond the scope of this class, so that's a nice cop-out I can use, all right? And it's true, it is beyond the scope of this class. You would want to take a statistics course. I don't know, they may teach a different method to do this, all right? I don't even know if they get into doing it by hand anymore, but I'm sure in most statistics courses they'll cover the theory and probably give you equations which you could theoretically use to solve by hand if you wanted to, but nobody does that nowadays, right? So this is just to satisfy those who are curious about how they used to do it back in the day before they had calculators. All right, so this is how we did it, and yeah, so read this book and it'll show you all the theory behind these equations and how they come up with those, all right, if you're really that interested. But first, well, before we wrap this up, let's get into the correlation coefficient. Yeah, you can calculate that by hand as well. Let me erase first. All right, so here's how you get R. And what I'm doing now you can do with any set of data if you want to get, if you have data which have a linear relationship, you can use this procedure with that data. Okay, so if you're really into doing this kind of stuff, be my guest. You can do it by hand. All right, so the square root of, this is getting complicated here, b sum of y's plus m sum of xy minus sum of y's squared Now this here is the total of the y column. You know, when you took all the y's and added them up, you put it in there and then you square that number. That's what that means. So don't square the y's, in other words. Don't square the y's. Now if you wanted to do that, the sum of y squared, the square would be inside the parentheses, all right? But we're not doing that. We're taking the sum of the y's, totaling those up, and then we're squaring that result. That's what that means, all right? Over, we have fractions inside fractions here, n, which was 10 in this problem, because we had 10 data points. And that put all that over the sum of the y squareds. Now here's, you square each y in this one, and then you add them all up. This one, you just add up the y's, and then you square the result at the end. Alright, so they are different. So let's see, minus, then we got the sum of the y squareds in parentheses, sum of the y's squared over n. So this is the same as that, alright? Take the square root of all this, alright? So I'm plugging in the data now. Alright, so we know what B is, we know what M is, in fact we know all of these things, alright? So all you have to do is plug and chug, as they say. Let me plug in the numbers here, negative 813, comma 800, 0.585491, times 55,734 plus 409.5027 16523 running out of ink here, times 111 comma 696 comma 294, and then minus minus what? Okay, that's over here, 55,734. And then you have to square that over 10. And that's over 364, 728, and 30, minus this again, 55,734, and then you square that, divided by 10. So you do all this computation, all right? Watch out for order of operations, okay? Once you get the numerator and the denominator, then you divide the result, and then divide the results, and then take the square root. All right. So let me write the fraction inside the radical here, just so you can, if you're doing this, you can check your work. Let's see, we've got 52,470,975.3 over 54,100,154.4, and then you take the square root of that. All right. And I'm going to round the answer to 4 decimal places like I did before, so you get 0.9848. Alright, that's exactly what we came up with before when we did the problem using technology. Alright, so that's our correlation coefficient. So again, this will work with any set of data you have to deal with. You can, with the rest of the examples in this section, you could use this method if you're so inclined, if you've got tons of time and nothing else to do, right? So I don't blame you if you don't do this, but this should satisfy your curiosity at least and give you a new appreciation for technology, because if it wasn't for technology, guess what you would be doing all night? This stuff, alright? So that's... I tell you what, when I took statistics back in the mid-80s, our professor, back then calculators were still kind of new, and there were a lot of old school professors around, and they did not like calculators, right? Because they didn't do it that way, they did it this way. And our statistics professor would not let us use a calculator at all. So guess what? He wouldn't even let me do arithmetic with a calculator. All right, I had to do all that by hand, everything by hand, including on the exams, including on the final exam, which was a bear. All right, we did it all by hand, and I'll tell you what, that was quite an experience. Well, there you go. That's how you do it by hand, back in the old school.